Okay. Okay. Welcome to everyone to this first seminar of the Magnetic Resonance Laboratory. We are back here in 2022. For this first talk, we have the pleasure to hear to Professor Abert Fert. He was his prize Nobel in physics in 2007. It's a pleasure for us that you are here now. So before to pass to the presentation, I would like to show this photo of Professor Fert at the 5th Latin American Workshop of Magnetic Materials that was in Bariloche. It was the first visit. I don't know if it was the first, but you are welcome to came here whenever you want again. And I would like to invite to all of you to pre-register to come to the international workshop on spintronic that is organized by the Institut Jean Lamour, by the Magnetic Resonance Laboratory and Riken Laboratory in Japan. It's going to be here in Bariloche in November. You're welcome to visit the official website. With that being said, I would like to pass to Carlos to continue with the presentation of Professor Fert.
Thank you, Luis. Thank you very much, Albert, to accept this invitation for my former group in Bariloche. I remember we met the first time in 2012, and the chairman just said, our next speaker doesn't need introduction. I think I can use the same word now. I will not introduce you too much about the trajectory. We are all magnetic community and spintronic, then we know your trajectory. Just to say a few words about your human quality. So it really was, it's my pleasure to work with you, and thanks again for all the support you give to your student, postdoc, and your colleagues. So with that said, it's my pleasure again to introduce Professor Abert Fert for the first seminar of this 2022 series in the Magnetic Resonance Laboratory. Go ahead, Albert.
Okay, thanks. It's for me now. Okay, I share. So we'll share the screen. Okay, so now you can see my screen, okay, yes. And you can hear me. It's too loud, not loud enough. Is okay?
It's perfect.
Okay, so good afternoon. I am very happy to be with you today. I thank Bariloche and Luis Aviles for the invitation. And so I have a very good memory of Bariloche when I was 20 years ago for a workshop, for a conference in Bariloche. And so I am glad today to meet many friends in Argentina, Brazil, and in many countries. And I thank Carlos for the introductions. So you can see the title of my talk, Spintronics, to go beyond conventional electronics and switch greener. And so not only better performance with spintronics and with conventional electronics, but also greener. That means, for example, smaller consumption of energy, which is a challenge of many of us today, reducing the energy consumption in our planet. By conventional electronics, I mean conventional electronics with semiconductor, the electronics we have in our computer, smartphone, and so on. And spintronic, you know what is spintronics? A new type of electronics manipulating not only current of charge, of electrical charge, but also current of spins, current of magnetizations, flow of electron transporting a larger number of spin with a given orientation of the spin. Pure spin current being the limit where the current carries only magnetization and no charge, no electrical charge. And about, you know that electronics has many applications. You know the first application where many sensors, the hard disk of the computer. And today, there are, what is in production today is logic and memory components like the MRAMs, the STT-MRAMs. So I show you an overview of the talk. So we begin with the first point, why go beyond conventional electronics, and explaining why it's interesting to go beyond conventional electronics. Then it will be a short introduction to spintronics for those that are not familiar, and the first development of spintronics. Then the main part of the talk will be on application, classical spintronic and application of classical spintronics, that is application of tunnel magnetization, spin transfer torque, spin torque for components like STT-MRAM, SOT-MRAMs, spin transfer nano oscillator, spin diode. And so the last part, if some time is left, it will be on another time, new direction of spintronics, skyrmionics, spintronic with skyrmions, and if time is late, I will say a few words on neuromorphic computing. So first point, why go beyond conventional electronics? First, to exceed the physical limit of classical electronics. And you know that we are after a stage where the Moore law were predicting an increase of the speed of the components every year, a decrease of the size. Now this Moore's law is saturating, is flattening off. And this is a limit of electronic with semiconductors. It's not possible to reduce the size because now if one reduces the size of this semiconductor component, the heating is too large. And so there are some limits of classical electronics that can be exceeded by spintronics. And then I show you two examples of objective in the that I want to develop for the fabricating low power logic memory components for our computer phones. That is the objective of reducing the energy consumption by all the digital technology and by all the technology of communication and information, and to reduce the significant contribution of this technology to the global warming. This is one of the aims of the physicists today. And so for example, you know certainly this sort of graph showing the percentage of the world production of electricity in the world as a function of time. And today, for example, all this technology of communication and information consume about 8% of the electricity production in the world. This is not negligible at all. And what is predicted with the extension of the data centers, the extension of all this technology is almost 21% in 2030. So is really significant. And with for our planet is really interesting to reduce this consumption of electricity, the consumption of energy. And to go to concrete examples, maybe you have already seen this picture showing that the consumption of energy, of electricity energy by Google is the same as the consumption by the town of San Francisco. And this energy, this number are from 2015, and there is an increase of the consumption of Google by 30% per year. And at our level, you can see that 30 Google search costs as much energy as to bring a liter of water to boil. So it's really interesting to reduce, to develop these low power components. And the second, on the right, what you can see, the interest of Spintronic also is to opening new type of technologies and new novel technologies, skyrmionics with skyrmions, manionics with magnons, neuromorphic computer inspired by our brain, and several other branches that are very, very promising. So now I begin with a short introduction on Spintronic and the first development of Spintronics. And so you know that Spintronic is based on the manipulation of spin currents in the ferroelectric, simply spin polarized current in a ferromagnetic metal with electron having the spin in the direction of the magnetization or in the opposite directions. What is known is that there is a different conduction by this opposite spin, parallel or anti-parallel to the magnetization. In fact, in first approximation, the conduction by two channels, spin up, spin down, with different conductivities. And this is a spin polarized current in a ferromagnetic metal or a ferrimagnetic metal. And now today, Spintronic use rather not only spin polarized, but pure spin current. What is a pure spin current? For example, pure spin current produced by the spin orbit coupling in EV metals, by the spinel effect of EV metal, platinum, for example. The large spin orbit coupling of these metals deflects the spins with at opposite direction in opposite direction, opposite spin in opposite direction. The red spin upward, blue spin downward. And if there is a layer on top of the platinum layer, that means this corresponds to the injection of red spins in this layer, blue layer here, and deflection and generation of a current of blue spin in the opposite direction for charge neutrality. That means that from this layer to this one, there is what one calls a pure spin current. That is a current, no charge current. There are the same number of electrons going upward and downward, but in fact, this the red spin are going upward and the blue spin downward. There is only a current of magnetization. And this can be obtained by the spin orbit effect in EV metals like platinum, but also by the what one calls the interfacial Edelstein effects. Carlos, you can remember something about the Edelstein effect, certainly. And this Edelstein effect is what occurs in some two-dimensional electron gas at hash bar interface between two materials or at the surface of interface of topological insulators. And the Edelstein effect is that a current in this two-dimensional electron gas generate a Edelstein spin polarization. And in the same way as above, the red spin will accumulate a red spin, will diffuse upward and generate finally the down spins will be attracted, and this is also a mechanism for generation of a pure spin current. And today in Spintronics, more experiments and also the most promising device are based on these pure spin currents. But coming back to the beginning of Spintronics and to the use of the simple spin polarized current in ferromagnetic metal. In fact, this has been first suggested by Mott and demonstrated later. In fact, the subject of my PhD was to check if really there was this spin polarization of the current suggested by Mott. And in fact, the results of my PhD, what really it does, and in a ferromagnetic metal, there is a more or less independent conduction by two channels with different conductivities, and so different currents in these two channels. And in fact, one of the results was also by a specific doping of the materials, the contrast between the conductivity of these two channels can be very large. For example, for 1% of this different type of impurity in nickel, the contrast between the conductivity of the two channels or the resistivity can be as large as 20. So that means that in some materials, you can have practically two-channel conduction with most of the current in one of the channel, and the second channel is practically blocked for the electrical conduction. And of course, if the magnetization is reversed, we are in the opposite condition. Now, the conduction is by the spin-down current, and the spin-up current is blocked. And this is the mechanism or the first spintronic effect, the GMR, giant magnetoresistance. What is the mechanism of giant magnetoresistance? If we have two magnetic layers, suppose opposite magnetization separate, for example, by a copper layer. In this situation, that means that this spin-up electron will be, we can go through this layer, but will be stopped by the second layer. And on the contrary, this spin direction will be stopped already by the first layer. But if is magnetic field, sometimes a small magnetic field can align the magnetization of the two layers. That means that this spin direction will be blocked everywhere, but there will be a shunting. A current can go easily through by the spin-up channels. And it works, it's supposed to work not only when the current is perpendicular to the layer, but also when the current is along the layers, because the trajectory of the electron is this sort of zigzag trajectory. So this is the principle of the GMR, but it works only if the distance between the two magnetic layers is shorter than the electron mean free path, a few nanometers. And at the time of PhD, it was not possible to fabricate multi-layers or tri-layers with very, very thin layer, a few atomic layer only. And so it was necessary to wait at the beginning of the nanotechnology. And then it was possible at Jülich in the lab of Peter Grunberg and in Orsay, in my group, to work this type of structures, a triatomic layer of ion, triatomic layer of chromium, and to discover the GMR. This is our results at Orsay. So the GMR is by applying a field and aligning the magnetization, there is a variation of 80% of the resistivity of the sample, and it was called GMR, giant magnetoresistance. And you know, the main application, the first application have been for sensor, but the main application is for the reading the information on the hard disk that is detecting the small field generated by the magnetic bits 0 and 1. And it's been possible with the sensitivity of the GMR to read smaller bits and to put a much larger number of bits in the same disk. And this leads to an increase by a factor of 1,000 of the capacity of the hard disk. And for example, this gives a boost to the, for example, to the data center with this type of hard disk with a huge capacity of informations that is at the base of all the data center in the world today, and sometimes in your computer too. So to summarize and to see where we are going now in Spintronics. So Spintronics, the birth came from the encounter between physics, spin and conduction, and the beginning of the nanotechnology. And after the giant magnetic resonance give rise to several applications, the compass, for example, the magnetic sensor, the hard disk, the compass. In my phone, I have a compass based on GMR. And to the development of spintronics and classical spintronics, I will discuss some application, low power application of classical spintronics. And I will say a few words on topological spintronics, that is skyrmions, and maybe also neuromorphic computer. So now classical spintronics and the application like STT-MRAM, Esoterm. So in your computer, if you have a hard disk, not sometimes in some computer the memory is not a hard disk, but a flash memory. But in fact, when you switch on your computer, you store a part of the memory of the because the access time to the hard disk is too slow to work with the speed of the computer today. And so you store a part of the memory in the RAMs of the computer. So the semiconductor RAMs, DRAMs first. And so there is several categories of RAMs, depending if it's only to store some information or to communicate rapidly with the logic gates. And for example, it goes from DRAMs to SRAMs with a very communication time smaller than the scale of the nanoseconds in the logic gates of the computer. And the disadvantage of these RAMs is that they are volatile and you need energy to maintain, simply to maintain the memory alive. And this is one of the main sources of the energy consumption in the computer. And also sometimes for some is also, it takes some energy to write and to read the RAMs. And so the objective with the Spintronics and with what we call the MRAMs, magnetic RAMs, is to have non-volatile memory, with no necessity of some energy to maintain the memory alive and also to very low energy consumption. And so, for example, among these MRAMs, the STT-MRAM are already on the market. I will give example. And tomorrow there will be the next generation will be SOT, spin orbit torque MRAMs. And for example, I can show you this some announcement of production of MRAMs by several companies. For example, Taiwan Semiconductor Company and also Samsung. For example, if you look on the commercial of Samsung, you can see that he has introduced his memory in some smartphone, for example, to reduce the energy consumption by a factor of 400, and with the access time 100,000 times faster. So there is some interest to introduce this type of memory in the market technology. And so what is a STT-RAM? STT-RAM is based on the STT-RAM is a sort of tunnel junction, two magnetic layer, reference layer, and a free layer, separated by a barrier, a tunnel barrier, for example, MgO, magnesium oxide. And the effect, the TMR, the tunneling magnetism is something like the GMR. So the resistance for the electron tunneling cause MgO, the resistance of this tunnel junction is very different for the parallel and anti-parallel configuration of the magnetic layer. And so this leads to this sort of device, very small device. You can see a image, electron microscopy image with a diameter of this pillar of only 20 nanometers. And the state of the memory is correspond to the parallel and anti-parallel configuration of the magnetization of the free layer with respect to the magnetization of the reference layer. And so reading is made by looking at the tunnel resistance of the tunnel junction, and writing is made by using a very, very interesting effect introduced by John Slonczewski and Luc Berger, the spin transfer torque. What is the spin transfer torque? Yes, in fact, it can be illustrated by this animation. When you send a spin porous current or a spin current into a magnetic material, the spin transfer torque means a transfer of the magnetization carried by this current to the local magnetization of this magnetic element. And so it can be used, transporting magnetization by an electrical wire can be used to change the magnetization, for example, the magnetization of this free layer from this orientation to this one. So in fact, the STT is very interesting effect for the development of low power spin and logic component. And so main advantage of the STT-RAM, non-volatility plus spin transfer torque writing, low energy consumption. And so, in fact, this is not the first generation. The STT-RAM has been exist on the market since 5 years, 4 years. Before there was a first generation, without STT, so no very efficient. But since 2006, there was only MRAMs that were used a large part of the electronic in the planes, avionic and aerospace, because these MRAMs were not very efficient, but were there was have a non-sensitivity to the radiation in the atmosphere. And so there was a niche market, interesting niche market. But now the market is much larger with the STT-MRAM. And for example, this is again the announcement by Samsung of the performance of the STT-MRAM, 1,000 times faster than the flash memory it replaces in the cache memory of telephone or computers, and also a reduction of the energy consumption. And for example, this flash memory, this STT-MRAM memory of Samsung are in some telephones and some, for example, in the Huawei GT2 smartwatch. If you have this sort of watch, you have STT-MRAM inside the. Okay. In fact, the present generation on the market is the STT-MRAM that gives rise to a strong reduction of the energy consumption. The generation will be Esoterm, so that is not based on the spin transfer torque generated by a current in the magnetic junction by the pure spin current generated by spin orbit effect, for example, in platinum or okay, so this is for Electron effect, but it can be simply the spinel effect in this layer generating a vertical pure spin currents to finally replace the, okay, compared to this system here, the spin current is going upward and consumes some energy in the tunnel, in the high resistance tunnel barrier. And here, in fact, the current is horizontal to give a vertical pure spin current, and so with a smaller joule heating in this layer. And so this is the base of the Esoterms, for example, is a topological insulator or a Rashba interface, Electron effect generating a spin polarization here to induce a vertical current to reverse by spin transfer torque the magnetization of this layer. And so the main advantage is non-volatility and low energy consumption plus speed. In fact, with SOT, it's possible to reverse the magnetization of the free layer of this magnetic junction at scale smaller than the nanosecond. We expect to the Esoterm, one of the advantage of the Esoterm will be also the spin to hide or hide this type of Esoterm. So if I want to present all the evolution in the same slides, at the beginning in 2006, there was the MRAMs, the classical MRAMs for avionic and spatial technology. Today, we have the Esoterms, STT-MRAMs here, with time scale of the order of a few nanoseconds, and so size down to, for the technology, to 40 nanometers, and so this consumption of energy per bit. The next generation will be, and so this, the next generation, these STT-MRAMs are integrated mainly what is called the cache memory of the computer. The next generation will be working at smaller, larger spin, so with the time scale smaller of the order of 500 picoseconds this time, smaller size, and also a reduction by a factor more than 10 of the consumption of energy. And so this new type of Esoterm are expected in the generation to be integrated not only as cache memory, but also in close connection with the logic circuits, what is called a complete integration between memory and logic, what is called processing in memory. And so this is the next step, certainly, for reduction of the energy and increase of the speed of the computer. And what you can see on the right is another type of device which is called MESO. So is MESO a concept introduced by Intel, and we are developing, working with Intel in a MESO projects to develop this type of logic and memory device that with a performance which will be better in terms of speed, in terms of energy consumption, and in terms of size. So I will say a few words on this type of MESO projects we are developing with other laboratory and with Intel. And so this is a presentation by Intel, in a paper by Intel, of the MESO low power logic components. So ME is for magnetoelectric, SO is for spin orbit. And so the argument is that if one wants to see what are the smaller power consumption that can be achieved according to the law of physics, it will be according to this study at Intel, it will be by magnetoelectric switching, that is switching by using ferroelectricity, using multiferroics and spin orbit detection of states. In fact, in this sort of components, the central element of this component is this one. In fact, the input current of this element is acting by the input voltage is acting to orientate, to polarize the ferroelectric polarization of a multiferroic, which is at the same time ferroelectric and ferromagnetic. And so there is a direct connection. So the input current polarizes the ferroelectric order, which polarize at the same time the ferromagnetic component order of this multiferroic that by interaction with magnetic layer can control the orientation of the magnetization in this layer. And then to read this information, this magnetic information, this read currents is transformed by charge spin to charge conversion by the inverse Edelstein effect. In fact, in the same way as the Edelstein effect is that a charge current can be converted into a spin current, the inverse effect exists also, that is the spin current produced by this ferromagnetic layer can be transformed into a charge current and output voltage by a spin orbit effect. In our situation, in the project we are developing, we are working on this conversion part of the device, that is the transformation of the spin currents into output voltage by a two-dimensional electron gas at the interface of the oxide, strontium titanium oxide. STO. And so, you know, we are, I describe this, I don't know if this Intel is relatively optimistic. I am a little less optimistic. We are working on another device of this type where now the ferroelectric polarization of this element is transmitted directly to the two-dimensional electron gas to inverse the charge spin to charge conversion of the electron gas. But I don't want to give more details, it will be too complex. And so with all this evolution of the spintronic device, hopefully we will be able to reduce this strong increase of the electric, of the consumption of energy, of electricity in the world. In fact, this device can be used not only for RAMs, random for MRAMs, but also for as application, radio frequency spin oscillator and spin diodes. And so, in fact, this is again the schematic for STT-MRAMs. and in which the spin current crossing the magnetic layer, the tunnel junctions, is used to reverse the magnetization from parallel to anti-parallel to change the state of this memory element. This is the basis of the STT-MRAMs. But in some other condition, this spin transfer torque on the free layer can be used not to reverse the magnetization, but to induce precessions of the magnetization of the free layer. And this precession, of course, give rise to oscillation of the resistance of the tunnel junction and to give rise to a voltage in the range, in the microwave frequency range. And so a RF signal. And so this is the principle of the spin transfer oscillator, spin transfer nano oscillator, that from this sort of pillar is possible also to produce, to have an emitter of radio frequency radiation. And so this is one of the applications, certainly, that have been developed and so can be very useful with a broader range than the usual semiconductor oscillators. So this we are developing also device of this type. And also the inverse effect is that by sending to this sort of pillar a radio frequency signal, is possible to induce this precession and to transform then and to convert this precession into a voltage between the top and the bottom. And this is what is the principle of the spin diode for conversion of a radio frequency signal into DC voltage. And this sort of thing has already application. In fact, some neuromorphic computer combine these two sort of device. And one as simple as application to understand is for harnessing the ambient air phase signal. In fact, in your room or in a place today in the world, you are in an ambient radio frequency signal coming from the telephones, from the Wi-Fi emitter, and so on. And so the idea is there is some energy to harvest from all these signals around us that you have in your room, even in your apartment. And so one interesting application is this harvesting of ambient RF signal. And for example, this is a device developed in Japan in the group of Hideo Ono, that with a sort of device with only 8 pillars of this type, nanopillar of this type, is possible to feed, to have the DC energy, the DC voltage to light this LED. And so, in fact, this can be very interesting to replace in many devices, in many sensors, the battery, the chemical battery, by simply this device harvesting the air phase signal around us. Okay, so after this example of application of classical spintronics and how they can be used to reduce the energy consumption and to a better use of all the source of energy we have around us. I will go to the last part, skyrmion and maybe neuromorphic computers. So what is a skyrmion? A skyrmion supposes a magnetic layer with magnetization upward. A skyrmion is a local configuration of the spin represented on this image here. This is an real skyrmions in which the magnetization is going from up, like on the layer on the edge, is rotating in this situation clockwise by going to the right, clockwise, becoming down at the center and continuing, going on with the rotation counterclockwise, the same counterclockwise rotation to become up. And so this configuration of spin is what is called topologically protected. So the concept of topological protection has been introduced by Mr. Skyrm in particle physics. But the first example of topological protection in condensed matter come in magnetism, particularly from the discovery of magnetic skyrmions in 2009 at the University of Munich. And so the topological protection come from this configuration with a continuous rotation in the same direction. It makes that this configuration cannot be unfolded continuously to come back to the classical ferromagnetic configuration. So there is what is called a topological configuration of this state once it has been established. And it is characterized by a topological number that you can write here. And what is the origin of this configuration? The origin is generally, not everywhere, but in generally, in most situations, is due to the antiferromagnetic interaction called Gialoshansky-Moria interaction. That is interaction of this type, cross product of two neighbor spins point a Gialoshansky-Moria vector. And so this interaction makes that the energy is opposite if the rotation from S1 to S2 is clockwise or counterclockwise. And so it makes that this energy stabilize this sort of configuration here. And so, in fact, this Gialoshansky-Moria interaction is due to spin-orbit effect, is a relativistic interaction due to spin-orbit coupling. And what is needed also for the existence of this interaction is no inversion symmetry. And so this absence of inversion symmetry can be obtained in non-centrosymmetric lattice. And in fact, the Gialoshansky-Moria interaction has been discovered at the time of Gialoshansky and Moria in non-centrosymmetric oxides of this type with super exchange interaction between the magnetic atom across in the oxide across oxygen. And so it exists, this skyrmion. We can see an image of this skyrmion in this sort of compound here, non-centrosymmetric. And in fact, it can be the breaking of inversion can be obtained by introducing interfaces between two materials. And typically, we can predict this. In fact, we have introduced this concept of Gialoshansky-Moria due to breaking of symmetry by disorder of interface with Peter Levy in first for disorder alloy and then a few years later at interface. And that means that, for example, at an interface with platinum and cobalt, due to the existence of large spin-orbit coupling in platinum and also inversion symmetry broken by the existence of an interface, there is symmetry between the top and the bottom of the system. There is a spin-orbit Gialoshansky-Moria interaction with this vector, blue vector, and favoring the rotation of the spin either clockwise or counterclockwise. And so this is that the most skyrmions are today are obtained by using this sort of symmetry breaking, inversion symmetry breaking in bilayer or multi-layer of EV and magnetic materials. And the property of these skyrmions here is that can be put into motion by an electrical current, as you can see here. And this is the base of many applications of in skyrmionic of these skyrmions. And so many experiments in the recent year have been performed in this sort of multi-layer with magnetic layer between EV metals. Not platinum cannot be above and below because the inversion symmetry now is restored, but with different metals above and below the platinum. And so maybe some repetition of this system to obtain couple of skyrmions, column of skyrmions that can be easily manipulated and are stable at room temperature. And typically images of these skyrmions with the diameter are between 30 and 10. Now we begin to prepare some skyrmions at below 10 nanometers. Okay, and so I will be rather short and fast in my presentation, simply to say that, in fact, these kernels can be also nucleated and created by current pulse. In fact, in the presence of spin currents, there is some spin transfer torque on the spin, and this and this spin can breaks the existing configuration, domain one, for example. And finally, at the end, what is remaining is the configurations that are stable by topology, that is the skyrmions. So simply sending a pulse of current into a magnetic layer, if there is also some spin recoupling below, induce this, and it can be done not only at random, but also at a given position in the device. And the scheme can be detected by the anomaly Sol effect. In fact, if in this cross here, if there is a skyrmion here, the voltage between lateral voltage between V plus and V minus will be different because the magnetization will be not the same in the center. You can see, for example, the variation of this voltage depending on the existence or absence of skyrmions in the cross at the center of the crossbar. And for the velocity, for the motion of these skyrmions, the most convenient way to move these skyrmions is to use the spin current, the pure spin current generated by the plate layer below the magnetic layer. And so the spin transfer torque generated by these spin orbit currents, for example, generated by spinel effect in this layer, is able to move, to put into motion the skyrmions. There is some problem because the motion is not exactly longitudinal, but I don't want to discuss the problem. Simply to mention that the velocity can be very large, of the order 100 meters per second. That means that nanoscale length 20 nanometers can be covered the size of the schema in the time scale of the picosecond. And so these fermions are also at the base of interesting applications. So in fact, one of the applications which is well known and has been developed in many groups without practical results so far is to replace the hard disk, which is very interesting by the large capacity of information it can contain, but also with some fragility due to the energy consumption due to the mechanical system to read the information. And now one of the projects is the restrict memory that had been tried sometime with domain wall, but it seems that now most of the work of the attempts are to make a restrict memory with skyrmions. That is a system in which the information is not fixed on the disk, but is stored in a sort of train of skyrmions that can be writing at this end of the channel and read at the other end. So this is the principle of the restrict memory on which many groups are working today. I don't know if suppose that will be some practical results soon. And there are many devices that have been proposed of skyrmions. The field of research has been very active. And for example, even logic gate based on skyrmions have been proposed. And some groups have been developing this type of device in which in a logic gate, the input signal and the output signal are not electrons, current of electron, but some skyrmions, current of skyrmions, like this current here. And so the transformation, several concepts have been proposed for several types of gates where the input signals and the output signal are skyrmions. So replacing simply in this sort of device the electron by the skyrmions. This is, I don't know, this certainly is not really to work practically, but, and in fact, simplest application can be simply to have a skyrmion MRAM. In a classical STT-RAM, there are two states corresponding to the parallel and anti-parallel configuration of these two layers. And switching from one to is made by using spin transfer torque to switch this orientation to this one. but this could be done also with skyrmions, simply by moving a skyrmion from outside in the bottom channel to inside the tunnel junctions, and so to switch with this low power switching by, it does not cost a lot of energy to move the skyrmions to reverse, to change the state of this memory. And the interest is that it can be done not only with one skyrmion, but several skyrmions. And so this corresponds to what is called a multi-cell memory. So there is also many interesting projects that are being developed with skyrmion in this way. So I don't know if I have some time. Since some time we'll have, I suppose I can take maybe 1 or 2 minutes to say a few words on neuromorphic computers. You know, certainly you have seen already this picture of the game Go between a Korean player and the computer AlphaGo. And the winner has been AlphaGo, but you can see a difference with that the computer was a very computer with a large energy consumption, 150 kilowatt, much more than what is used by the Go player, which is 10 to the 4th smaller, only a small piece of sugar for the brain of this guy. And also this guy can do much more than only playing Go. He can also sing, write music, and so on. And so there is, in fact, at the same, you can see the priority of the brain, of our brain, on the computer of today. And why? Why? In fact, if we want to understand what are the general bottleneck of the computer of today, of the digital computer, is that in fact in the computer of today there are logic elements, logic circuits, and memory, and there is a back and forth exchange, continuous back and forth exchange between the two, between processing and memory. And this is what can be called von Neumann bottleneck, separation between memory and processing. Very hungry back and forth exchange of data between. And also there is non-scalable. You cannot change, there is always wiring connection between memory and logic. And this is not very flexible and configurable. And the difference in the brain is that, in fact, the signal as transmitted, a given signal is transmitted from neuron to neuron across synapse. And at the same time as the signal is transmitted, the transmittivity of the synapse change. So at this time, you have not only transmission of the signal, but a reconfiguration of the circuits. And there is and at the same time, the memory subsists in the synapse. So there is at the same time, not only transmission of the signal, but not only processing, but also memorization, and reconfiguration of all the circuits. So finally, this explains that our brain is, in terms of energy, for example, not only is much more frugal than the digital computer. And of course, the interest of what is called neuromorphic computing, imitating the computing in our brain, is understood, has been understood for a long time. And so there are always several neuromorphic computers working in the world, many neuromorphic computers. But for example, I take the example of this neuromorphic computer developed by IBM, the True North neuromorphic computer. In fact, there are synapses and neurons, but artificial synapse. What is a synapse in this computer? A synapse is a sort of microcircuit with about between 50 and 100 transistors with a big size. not on the size nanoscale, but at the size micron. And so, and also the neuron also are made with many transistors. Finally, this leads finally to the size of the neuron is very large. It's made with many computers even. And so finally, you can see the limit of this sort of approach if the small synapses, the synapses are big. The technology to big size and large energy consumption. There are too many transistors, and the space taken by this transistor leads to very big size. If you want to reproduce simply the number of synapses and neuron in the visual system, you have finally a computer that at the size of a stadium, and so. And also CMOS technology does not provide memory. And so what can be done is to the future is simply to develop, don't use classical electronics to imitate synapse and CMOS, but to develop purely synapse and neuron components at the nanoscale. And this is done in particular in my lab by Julie Grolier. And I have the time to give more details. Future of physical computer, nanoscale component acting individually as a neuron and synapse at the nanoscale. And there is two examples. I give you simply the reference of publication. I have another time to give into details. So this is a paper in our group, in our lab, on ferroelectric synapse that have been developed in several companies. So there is still problem with ferroelectricity. So it's not maybe the most interesting direction. And this paper is neuromorphic computing with nanoscale spintronic oscillator, the type of oscillator I have already described, that is emitting a radio frequency signal due to the precession of magnetization. And this, certainly this, and the transmission between these neurons is by RF emission. So there is wiring is very simple also. And so this system seems to be really a very interesting direction for the future of the development of this sort of neuromorphic computer. In fact, and it has been already applied to tested on the driving of autonomous vehicle, autonomous cars. And in fact, it appears also that in this case of autonomous car, today with the usual computer, the energy spent to consume to drive the car is 1/3 of the energy for the motor of the car. And so with this, the energy can be really realistically reduced in this sort. In fact, all the development in my lab are by Julie Grolier, a new star of the physics and certainly in France, it has been Femme Scientifique, scientific woman of the year 2021, all category of science include. And so what I have in mind is that probably certainly after Marie Curie that got the Nobel Prize, maybe it would be second French woman for the Nobel laureate, to be Nobel laureate. So certainly what she is doing is very bright today. So the end of my talk. So there are continuous advances in spintronics, and this will lead to go beyond electronics and to switch greener too. This is advances between the GMR to what is done today with neuromorphic computer. And this is the end of my talk. And I thank you for your attention.
Thank you very much, Albert, for your beautiful talk. For tell us something about the different pathways of the spintronic towards a greener technologies. I would like to open the session to questions. I think we can start with the people that is in the Zoom channel. You can raise your virtual hand and then pass to the question of the audience in the conference room in the lab.
So I keep the frame or not? I leave the full.
As you prefer. If you prefer.
No, no, as you want. I don't know.
And you can keep it if you want for a moment.
Oh.
Yeah. Okay, I can start with a question while other people want to ask. Okay, what do you think about the role of ferrimagnets and antiferromagnets in the new spintronic device? You know, in the recent years, there has been a lot of research in the ultra fast control of magnetism using ferrimagnets and antiferromagnet, but it seems that there is still no a ferrimagnetic material or antiferromagnetic material as the core of a spintronic element. What can you say about that?
So I can tell a few words. Okay, I know more the ferrimagnetic material, and I think, and I push it a lot in my lab to work in this direction, and I work with Carlos too. And so these ferrimagnetic material are very interesting for several aspects. First, all the magnetic material of today are with small spin-orbit coupling. And so generally, many devices are based on the combination of a low spin-orbit magnetic material like iron or nickel or permalloy, and below the spin-orbit is taken in another layer of platinum or something like that, or topological insulator. And so the advantage of ferrimagnetic material that most of them, many of them are based also combine 3D materials like cobalt with rare earths, and rare earths have a 5D band of large spin-orbit coupling. So you can combine, you can have both elements, magnetism and large spin-orbit coupling in the same material. And so I guess there are many interesting from this point of view. The second point is that in a ferrimagnetic material like those I worked with Carlos on this, is that you can introduce some gradient. There are automatically PMA, that is perpendicular magnetization, and you can also introduce some gradient in a single layer, some gradient of composition to introduce at the same time the inversion symmetry breaking needed, for example, for dilatation Schemeria interaction or for Rashba effect. And so we have a lot of possibility with this ferrimagnetic that you cannot have with the usual cobalt-like materials. And so I think they are very interesting. In fact, also you can also tune the magnetization to have a small magnetization and for the same torque, and so with the same spin transfer torque, is easier to reverse the magnetization when the magnetization is close to the what is called the compensation point of the magnetization, where there is compensation between the magnetization of the 3D magnetic material and the rare earth element. So there is a lot of advantage. And recently, in my work in collaboration with several groups in China, in Italy, we could also, with a layer of gadolinium ion cobalt, with some artificial gradient of composition, to obtain the switching of the perpendicular magnetization without applying a magnetic field. It's necessary usually. So I am very optimistic about the potential of the ferrimagnetic material. For the antiferromagnetic material, I don't know very well. So I have not really an expert point of view on the antiferromagnetic material.
Thank you. Thank you. We have a question from Sergio Resende.
Thank you, Albert, for your great talk. They're usually good, but this one, for me, it was especially good for several reasons. The question is, for over 10 years, we have been reading and hearing people saying that spintronic devices would replace CMOS technology. But of course, CMOS technology is very efficient for logic operations. In the last part of your talk, when you talk about neuromorphic computing, are you mentioning actually full logic operations integrated with memory that have a real possibility for replacing CMOS technology?
Yeah, the integration with CMOS technology has been done in several devices. For example, it has been demonstrated in the last paper of Julie Golier that this technology with pillars for spin transfer oscillator is easily integrated. She has demonstrated that she could integrate this technology on CMOS. So there are some problem, but in most, I know many examples of good integration of both technology, spintronic and CMOS.
So you mean integration?
Yeah.
The magnetic part would not replace the logic operations of the CMOS. They would be integrated.
Yeah, but the future is for a complete integration between logic and memory, as I show in one of the So what can be expected here is finally the final is processing memory. So complete integration to avoid this bottleneck of exchange between memory and logic. And this exists in some system already, and this will be really, if we want to go further and not stop at this stage, it will be processing memory, so integration. And for example, in this element, there is a complete integration. MESO, there is no difference between memory and logic. These sort of systems,
Okay. Yeah, I understand.
This sort of system, you have, this is a memory gate, which is also memory and gate. MESO interconnect with cascade gate. So all these projects we are working on with Intel are in the spirit of what I call processing in memory. So complete mixing between the two.
Okay, thank you.
Thank you, Sergio. I think we can pass to the questions in the conference room. Carlos, are you there?
Yes, maybe I have a question.
Okay.
Albert, concerning the skyrmion for application, is there a limit for the speed to moving this skyrmion, or what value will be useful for application?
Oh, the speed is 100 meters per second is enough. Okay, as I show in one of the slides.
Yeah, 100.
Yeah, 100 meters per second, and so that means that your device at the nanometer scale, that is 20 nanometer between two elements. This is the minimum, and you cover this distance in 200 picoseconds. So you are already faster than with the CMOS technology today. You see, this is a simple calculation. Yes. 100 meters per second, you can go on a distance of 20 nanometers in 200 picoseconds. So,
yeah, I don't know if you are aware, in Yassin Kesab in NYU, they show a speed up to 600 meters per second using ferromagnet, by the way.
Yeah, yeah. You mean skyrmions for a skyrmion?
Yeah, for a skyrmion. But
Yeah,
I think
yeah.
it's quite bigger, the diameter of the skyrmion.
Yeah, yeah. So this one is for small skyrmions of the order of 50 nanometer. But now there are, this is not a recent result. There are more recent results with smaller skyrmions and faster velocities.
Thank you.
In fact, with domain walls, there are now some velocity of 3,000 meters per second. In fact, if you consider this type of velocity is faster than the electrons in AY with a general normal density of current.
Okay, thanks. We have a question from Horacio.
Yes, my question, it is clear to me to what degree will quantum coherence be needed in those devices? How much?
Quantum coherence, yeah. So generally, in which case there is a need to quantum, let's remember, generally, okay, quantum coherence is not really involved in most results that are presented. So, no, really, quantum coherence is not the main, okay, there is nothing on quantum coherence in what I present. I try to understand, there are some examples of quantum coherence is important, but I have nothing in mind today to a clear example of what quantum coherence is important. So it's not, no, it's not the main point quantum coherence in all these things. In fact, all these effects are correspond to an average value of an electron gas, of a skyrmion gas.
Thank you very much.
Quantum physics is involved, but not quantum coherence. Quantum physics is involved everywhere, but
we have a question in the conference room. Carlos Ramos, could you pass the question?
Bueno, no, yo quería preguntar un poco, para generar, oh, sorry, in English. I want to ask, to generate microwave or radio frequencies, you need a magnetic field involved in the...
No.
No, okay.
No, there is no magnetic field, no. In fact, it is always in all these applications, is better to have no magnetic field. By fabricating a magnetic field with the core it cannot be done easily at the nanoscale.
Thank you.
Thank you. We also have a question from Ale Colton, I think.
Yes. Okay. Thank you very much for the talk. Very nice. I have a question about also application of skyrmions. I wonder if there is some application for skyrmion lattices. I mean, so far that all the examples I saw are manipulating single skyrmions, but you can also have an interaction between them and skyrmion lattices. I wonder if there is some application for that.
The application of skyrmion lattice are not very attractive because a skyrmion lattice is a big lattice, and so in fact it's not nanoscale. Okay, so it's better to have a single skyrmion that can manipulate like an electron. Okay, the skyrmion, yeah. So I don't see real application of skyrmion lattice.
But even in a track, you can have many skyrmions very near each other, and maybe interactions.
Yeah, the interactions are important. Even for single skyrmions, one knows the interaction. One knows that there is a repulsion of a skyrmion by another one, and so that the distance of the you cannot the distance must remain if you have no strong energy to approach them. the distance can be only on the range, on the size of the skyrmions. So finally, in this application with skyrmions, you cannot have the distance between skyrmions is more or less the size of the skyrmions. But with lattice, what to do with the lattice?
No, maybe phase transitions for a skyrmion.
Yeah. Yeah, for phase transition, yeah, you can. But most developments, applied developments I know are with single skyrmions, to play with skyrmions as one plays with balls.
Okay, thank you.
I have another question. Is there any strong research in STT-MRAM, or is or everyone is migrating to SOT-MRAM?
Yeah, I have no. It's not my expertise, the integration of into real CMOS systems. But I know that, for example, in Grenoble, you know, Dieny and Lucian, they are working on this sort of problem of integrating STT-MRAMs on CMOS systems.
Yeah, they are starting to work on the development of SOT-MRAM, but it's a really promising area, as you mentioned in your talk.
And also, the example of, for example, device I have shown somewhere. In this sort of device. Okay, so the integration on CMOS already exists because, for example, if you buy this watch, smartwatch from UI, you have a system with integration of STT-MRAMs on a CMOS array. Huh? So like here. So you can buy already some watch or some phones where you have MRAMs. In fact, the problem with is that if I have some number, so at the moment, most of the market, the largest market of Spintronic is hard disk. But the market of STT-MRAMs, with only a few companies have been able to have the strong enough investment to make fabs, fabrication factories of STT-MRAMs. So the production now is only 1% of the market is STT-MRAMs. The hard disk is 10% of the market of electronics, of digital technology. STT-MRAM is 1%, but what is expected according to some forecasts is 10% in 4 or 5 years. So progressively, this sort of device, like this watch of UI, will develop, and but it's difficult to. The electronic industry is so big that it's difficult to change the whole digital electronic industry in a few years. It will take, say, 5-10 years to change completely, significantly the electronic industry. I don't know if at the time of where all the trains were with machine of vapor, I don't know the name in English, but you understand. So the proceeding to the electricity machines took some time because it was a big industry and it's not easy to change rapidly a big industry. There are so many companies that have not the power of Samsung, of IBM, of Intel to invest and to change rapidly their technology.
Yeah, I understand. Thank you for the answer. Is there any other question?
So I can say that I am going out of my field, my usual field of expertise is physics. Huh? And so today I try to go further.
Yeah. Yeah. Is any other question in the audience or in the Zoom channel? Seems no. Okay. I would like to thank you, Albert, for your very nice presentation, for sharing your work with our group. And, I don't know if Carlos has some closing words, Carlos Rojas.
No, well, just to say thank you again, Albert, and thank you to the Resonance Laboratory, my former group. As Albert know very well, I did my PhD there, and I'm very happy that I could work there and then with you, Albert. Thank for all your support and for once again for accepting this kind invitation from the Resonance Laboratory, for the Magnet Resonance Laboratory. And I don't know, Albert, if you want to say maybe some last word, especially for our young students in physics, in magnetism.
Oh, yeah, young students. The time is difficult for young students because we cannot have today the same type of, with the COVID, the same type of direct relation that we have normally. And so it's difficult time for the students, I realize. And so, but soon again, we can have the same communication with the students that before, and it will work better. And Carlos, maybe a message for you. Have you some news from Nanogoon about these 2D magnets?
Not yet, not yet. But yeah, we can call. We can have a call later.
Yeah.
Yes.
Thank you, Carlos.
Okay.
Thanks again to all of you.
I would like to close this first seminar, and you all are invited to the next one. It's going to be shared by Antonio Acevedo from Brazil. So see you next time. Thank you, everyone, for your presence here.